All right, folks, I'm back again. Mr. Hess here to teach you about Section 4 in Chapter 7. The title of Section 4 is Parallel Lines and Proportional Parts. Okay, so what I'm going to show you then in this section, you might say, is kind of like a shortcut that we could use when we have a specific type of scenario. And that specific type of scenario is outlined here in Theorem 7-4 of your postulates and theorems. This theorem is better known as the triangle proportionality. And what it does is it defines that special scenario I was talking about. And that special scenario is when you have a triangle. And if in that triangle now, if you run a segment through the triangle that's parallel to one of the sides of the original triangle. So here's the original triangle. We run a segment parallel to, say, this bottom side, for example. Okay, so if you run a line parallel running through the triangle, what it does is the other two sides of that triangle, not the one that it was parallel to, but the other two sides, then are cut up into parts, and those parts will be proportional to one another. Okay, in the past, when we did a problem like this, because these were parallel, we could actually say the corresponding angles match, and then we would say the smaller triangle is similar to the bigger one. And then when you think of it in terms of small triangle, big triangle, in the past I might have said, for example, the ratio of the sides was 5 to this full length, 5 plus 2, or 7. So a 5 to 7 ratio. But it turns out you don't have to do that. You don't have to add these together to get that full length on the bigger triangle. In a scenario like this, when you run a parallel line, it does cut these into parts, and it turns out the parts are proportional. So instead of going 5 over the full length 7, I can just put 5 over the 2. So in this picture, I know that 5 over 2 will then be equal to the same pattern over here. So I went top over bottom, so I'm going to put top over bottom here. 7.5 over 3. I'm just going to put 7.5 as 7.5. So then I can do some math here now. Okay, I cross multiply. I want to just show you that it works, that these are proportional. After all, 5 times 3 is 15. And when I cross multiply that way, 2 times 7.5 is also 15. So you see it's a match. Of course, when you go to do these problems on your homework, instead of giving you all the information, all the sides, all the lengths, one of these might be missing. Maybe this one will be missing here, and they'll have you find that one. Maybe they'll call that X. So my X would have been right there. When I cross multiplied, this would have been 5x, and I would have had then 5x equals 15 divided by the 5, and my x is 3. No surprise there. That's the number I erased from there earlier, 3. Okay, so again, this is meant to be a shortcut so that we don't have to look at this as the small triangle is similar to the big one. And you don't have to think of this in terms as 5 and 7 for the full length, or in this case, when that was 3, you don't have to look at this as 7.5 being over 10.5, the full length. So it's a shortcut. Now there is a theorem 7.5 as well. Theorem 7.5 though is just the converse of this idea. Okay, so originally Theorem 7.4, if I give you caveman talk over here, would have just simply said something like this. If those are parallel, so if parallel, then these were proportional. So then proportional. Okay, that was originally 7.4. Okay, now Theorem 7.5, of course, being the converse, means we're just going to switch these two ideas. So Theorem 7.5 is something that you would use to prove the lines parallel. So if you could show that 5 over 2 equals 7.5 over 3, and if I did not know these were parallel to begin with, but if I can show they're proportional instead, then if they're proportional, it also proves that the line's parallel. Okay, so we'll rarely use theorem 7.5. There's no reason to really use that to prove lines parallel. Instead, we want to use the shortcut itself. All right, there's a theorem 7.6 on your list of postulates and theorems. Okay, in theorem 7.6, I'm almost surprised they didn't make it a corollary, because it's really kind of a special case scenario, a specific scenario of what we just discussed up above here. Notice up here, though, I had 5 and 2, but down here, what I want to do is, instead of it being broke up like that with a 5 and a 2, I want the two of these two, the two parts along this side to match. I want them to be congruent. Okay, same here. I want those two to be congruent. So instead of being different like they were up here. So in other words, on theorem 7.6, it says if you find the midpoint, since those two halves match, that's the midpoint. So if you connect the midpoint to midpoint on any two sides on a triangle, okay, then here's what happens. There's something special here, and it has to do with these sides now. I didn't even mess with those on this problem, right? I didn't even know these lengths or mess with them at all. But if you connect midpoint to midpoint, then the other two sides that are left here and here, they're going to have a relationship, and you'll notice it there that the 7 is exactly half of this one down here, the 14. Okay, so on any triangle, not this scenario up here, but on this scenario, if you connect the midpoint to midpoint, then that segment you just join the midpoints with will always be half of its one that's parallel down here. And that will be parallel too, by the way. Because after all, using theorem 7.5, we could show that those would be parallel, because no matter what these numbers were here, they would be proportional. Single over single is going to match double over double. No matter what you put in for numbers here. Like if that was a 5, it'd be 5 over 5. And if you put a 7 here, 7 over 7. It's always going to be the same ratio. So it's parallel, and it's half the measurement of that one down there. All right, now there's also a couple of corollaries. I'll flip my board over here to show you those. There's a couple of corollaries in this same section as well. There's a corollary 7.1. Now remember, corollaries are kind of like a cousin. They're closely related ideas, okay, just like a cousin's closely related to you and your family. Okay, and this corollary is like that cousin that likes to take things a bit too far. They decide, oh, hey, if this works, let's try this, and they go on a bigger scale, a grander scale. So on this corollary, we're going a step further than that first theorem I showed you on the other side of this board. This time, instead of just having the two parallel lines, they say you could have 3 or more. I've only shown you 3 parallel lines. You can just keep going with parallel line after parallel line. And then when you go ahead and draw your lines that are transversals crossing through those, then notice that each of these lines then is broken up into segments. Okay, and here I labeled this one A, this one B, and this one C. On the other transversal, I've got D, E, and F. Well, that triangle proportionality theorem we covered at the beginning of this lesson applies here as well. But now we're doing it on a bigger, grander scale. Instead of just saying, like on the other side, the old theorem said top over bottom equals top over bottom. Here now I can include and incorporate the C and the F as well. So any pattern is going to work here, in fact. You can make all kinds of proportions out of this. Instead of just going A over B equals D over E, which does work, that's a possibility. You could also do A over C. And see how I went very top over very bottom here? So I do the same over here. D over F. You know, as long as you're doing the same pattern, it's going to work. There's all kinds of proportions you can make up. You could even do something like this. You could say that I could take the A and the B and add them together and say A plus B over C. So I did A plus B over C, and that would equal D plus E over F, right? D plus E over F. So again, you know, as long as you're doing the same pattern on those, there's all kinds of possible proportions. You could go A minus C over B equals D minus F over E. You know, stuff like that. All right, so that's corollary 7.1. There's also a corollary 7.2, which is like a cousin of the cousin, you might say. What it does is it takes this last corollary 7.1, but this time the parallel lines that I made here, here, and here, this time we're going to space them out evenly. You know, on this one I did not necessarily space those out evenly. You know, you might be able to notice in my picture that B looks a little bit shorter than C in this one. So the gap between these was a little wider. But if I were to space these out, these parallel lines all out, and space them out evenly, okay, then, you know, beyond the usual ideas of this corollary, it goes a little bit further, a step further yet. So if I draw a transversal, what it does is, in between the parallel lines, it cuts each of those into parts, and all of those parts would be congruent. Okay, so this, and this would all match. On this transversal, that, and that would all match. The segments in between the parallel lines. In fact, the more I tilt this line, the longer they get. And if I want to make them as short as possible, I would have to have a transversal that runs perpendicular. If I run one at a 90-degree angle perpendicular, then that's the shortest possible segments that would all match. So that, and that would match, and they'd be as short as possible. Okay, I like to think, on that one, I like to think of this, when these are all spaced out evenly, kind of like a farmer when he's planting crops. You know, when he plows his field, the rows of corn, so to speak, or beans, you know, are all spaced out evenly. Okay, and as those blades go through there, they're already naturally spaced evenly. You know, imagine now if you had like a twig or a branch or something that was laying in that field, as you run over it with the blades of that plow, it's going to cut it into two smaller sections that all match. All right, so those are all the corollaries and theorems for this section. Now I'm going to jump into some problems. So I'm just going to go ahead and erase this side here. And let's make use of those postulates and theorems and corollaries we just learned today. Here's our first problem. Let's say that I've got a picture like this. Okay, and I've got a segment running here that is parallel to the bottom. Okay, so that satisfies the conditions that we needed for that first theorem that I covered in this section, that triangle proportionality theorem. Okay, and let's say that this is, here, I want to make that a little more accurate. Well, let's just do this. Let's say that's 8, that's 6, and let's say that this is x, and let's say that that's 15. All right, so if this runs parallel through there, okay, then that means that it cuts this side and this side into parts, and those parts will be proportional. So by that triangle proportionality theorem, I could say that this 8 and this 6 will have a ratio. I'm just going to put 8 over the 6, top over bottom. That matches the ratio of these two parts. So over here I put x over 15. Top over bottom, top over bottom. Just, pick a good pattern. Stay consistent. All right, now I solve this. Cross multiply, I get 6x here. 8 times 15 is 80 plus 40, 120. Divide by the 6. That goes into there 20 times. That means my top value up here that was missing, x, has to be 20. Okay? Let's try another. Call this one problem number 2. Again, these two are going to be parallel, just like on the last problem. Let's say that this top part is x plus 6, this bottom part is x. Let's say that this bottom part down here is 9, and this entire length of that side is 30. Okay? Obviously, I just made that one a little more complicated than our last problem. However, I will say, though, the approach is still going to be the same. See how here I knew that these parts were proportional to those, so I put top over bottom, top over bottom. I'm going to do it again. I'm going to put top over bottom, so I'm going to put x plus 6 over x. And over here I'm going to do the same, but I got to do a little math. I got to figure out, what is that length right there? Well, if the whole thing's 30, that part's 9, wouldn't it just be 30 minus the 9, or 21? So this part in here is 21, and I'm going to put a 21 over the 9 then, and set it equal to the ratio of these two. So top over bottom equals top over bottom. Okay, and then, like I did here, first step is to cross multiply. So 21 times x, that's easy. That's just 21x. Be careful going this way, though. You've got to take the 9 and distribute it times all of this, times the x plus 6. So we got to distribute that 9 times the x and times the 6. So our equation now becomes 21x equals 9x plus 9 times 6, or 54. This creates a Sheriff Bandit situation. Okay, I would normally tell people just to get rid of the smaller ones, so that would mean subtracting the 9x over to that side. Okay, that leaves us with 12x over here and 54 over there. Divide by the 12, and you have your x. X goes into 54. 12 goes into 54. How many times is that? That's 4.5. 4.5 or 4.5 on that one. All right. So there's a couple of examples. I'm going to try another one here yet. Okay, on this next one, see if this throws you off any. In our picture here, I'm going to draw it like that this time. And again, these two are parallel. So I've rotated the figure a little bit from what we were doing previously on problems. Okay, so be careful. Don't let that fool you. Let's see here. What if I told you then that this is 18 here, maybe a 6 there, 12 here, let's say, and x minus 3 for that part. Okay, because these are parallel, again, it's going to cut up the other sides into proportional parts. Okay, not the two that are parallel, but the other two sides here and here. So if these parts are proportional again, make sure you do the same pattern. Okay. Earlier, remember I kept saying top over bottom, top over bottom. We could kind of use the same idea again. if you just kind of look at it a little bit differently, tilt your head maybe a little bit here, and go, I'm going to go this over this, you know, the 18 over the 6. You know, I'm going to work my way to that same spot over here, you might say. So 18 over 6 equals x minus 3 over 12. Okay? Or another way you might look at it, you could say 6 over 12 equals 18 over x minus 3. You know, either one's going to work, you know, because look, first step you're going to do is cross multiply. So you're going to take 18 times 12. Look, 18 times 12. And you're going to take 6 times all of this. Look, 6 times all of that. So it doesn't matter. Either setup would have worked. And as long as you're consistent in your pattern, it should work. All right, here we go. 18 times 12. Oh, let's see, that's a big number. 216 is what that gives me. And then I'm going to take 6 times the quantity x minus 3, meaning I got to distribute the 6. So I'd have 6x minus 18. Okay, then you would add this 18 over here. You know, we're trying to get the x by itself. That gets us up to, let's see here, 14, carry the 1, 234. Divide by 6 yet, and you'll have your x. So let's see, 6 goes into, let's just use a calculator here. 234 divided by 6 gives you 39. So there's the value of x on that one. X would be 39. You could plug it in there. Of course, it would be 39 minus 3 or 36 for that length. Okay, but x is 39. All right, so don't let that scare you. If they kind of rotate the triangle, you know, don't let that fool you. I got one more problem I want to try with you here yet. And rather than giving you a picture, this one's kind of a word problem written out, but in triangle RST, suppose M is the midpoint of segment RS. Suppose that N is the midpoint of segment RT, and, or I'm sorry, that's supposed to be ST. Okay, and suppose that the point P is the midpoint of segment RT. Okay, and ultimately on this problem, they're going to want us to find the perimeter of triangle MNP if we know that RS has a length of 28, ST has a length of 34, and RT has a length of 30. Okay, let me read through that one more time. In triangle RST, M is the midpoint of RS, N is the midpoint of ST, P is the midpoint of RT. Find the perimeter of triangle MNP if RS equals this, ST equals this, RT equals that. Now, right now, it might sound confusing. You might think, oh, how am I going to do this? Let's just start out with a picture, okay? You know, we have our original triangle RST. And if you look at the very end here, they even told us RS had a length of 28 for that side. ST has a length of 34. And RT is 30. Okay, and then I'm going to go back up here yet and draw in all these midpoints. You know, they mention quite a lot of midpoints here. Midpoint, midpoint, midpoint. Okay, so M, they said, is the midpoint of RS. There's RS right here in the middle then would be our midpoint M. Splitting that into 2 equal halves. Okay, N is the midpoint of ST. ST, there's the middle of that, let's say. That's the point N. Here, I'm just gonna, let's do this. There, that's 28. That's 34, and there's that midpoint N. And finally, point P is supposed to be the midpoint of RT. So right in the middle of RT here is a point P. Now if we join those midpoints, M, P, and N, notice they make another little triangle in here. And what do you know? M, P, and N, okay, are the same triangle that they want us to find the perimeter of. Okay, so they want to know the perimeter of that little triangle inside of the bigger one. Okay, we've got to do this problem, we've got to utilize one of our theorems that I covered earlier. Okay, and to help you focus on it, what I'm going to do is I'm actually going to erase those 2 segments for right now. Okay, do you remember we had a theorem, I think it was, let's see, 7-6, theorem 7-6 I covered earlier. That said if you join the middle of one side to the midpoint of another, that segment that you make there will not only be parallel to this down here, but its length, remember, will be exactly half. So see, if this is 34 all the way down here, that full length is 34, then this should be exactly half of the 34. So half of 34 is 17. So that length there would be 17. Okay, and we keep using that idea over and over again. So see, PN, if I join those midpoints, not only is that line parallel to this one over here, but it's also half of its length. So half of 28 is 14. Okay, I join M to N, midpoint to midpoint. Not only is it parallel to that, but it's half of its length. So half of 30 would be 15. Okay, and then finally, if I want to know the perimeter of the triangle in the middle, all I have to do to get that perimeter is add up all the sides. So I'm going to add up 17, 15, and 14. 10, 20, 30, 39, 46. There's the perimeter of the triangle. Which, by the way, if you want a bit of a shortcut even, if you know that all 3 of these are going to be half of all 3 of these, you could have, as a shortcut, you could have found the perimeter of the bigger triangle. You could have just added up all 3 of those and just cut that perimeter in half. You know, the perimeter of this smaller triangle, 46, should be exactly half of the perimeter of the bigger one. There you have it. That's all the types of problems that you should run into on your homework as well. Let me know if you have any problems, though. You can text me on Remind or send me an email if you need some help. And don't forget, again, I hold office hours on Monday, Wednesdays, and Fridays at 3 o'clock. So if you do need some help, you can join me then on Zoom. Just look for the invite in your email.